Hello, my name is Bill Thompson. I'm a faculty member at the University of California, Irvine, and this video is part of our series that's a lawyer's guide to probability and statistics in forensic science. This video series is supported by the Center for Statistics and Applications in Forensic Evidence, or CSAFE, which in turn receives support from NIST, the National Institute of Standards and Technology. The goal of these videos is to help lawyers understand the numbers that forensic scientists use to characterize the strength of their evidence. It's also designed to help lawyers understand non-numerical statements that forensic scientists may make that are based upon a statistical or probabilistic analysis. Even statements that don't look like they're statistical or probabilistic sometimes have a probabilistic basis that lawyers need to understand and evaluate. And these videos will help you do that. There are three videos. Each of them is focused on a different task that forensic scientists perform. Video 1, part 1, is on quantification. So when forensic scientists try to determine the quantity of something, for example, how much alcohol is in this blood sample, that task often requires an assessment of statistics and probabilities. We'll talk about that in part 1. The second video focuses on a different forensic science task of classification, where forensic scientists are asked to examine something and determine something about it to classify it. Is this white powder cocaine, for example? Put it into a category. That also involves statistics and probabilities quite often. The third task that we'll talk about is comparison and identification, when a forensic scientist is asked to compare two items and determine if they have a common source or a different source. So did this evidentiary sample have the same source? Did this latent print come from the same finger as the reference print? Did this DNA sample come from the same source as the reference sample? And so on. So those are the three tasks we'll be looking at. This video is part 1, looking at the first task, quantification. For the first task, quantification, there are three major issues that lawyers need to think about. One is validity. Is the lab measuring what they think they're measuring? The lawyer should be looking for a published scientific literature that establishes that the method being used for measurements is a valid method that does what it claims to do. A second issue is calibration. How well do the measurements made by this method align with the values of known standards? And again, here lawyers should be looking to see whether the lab has as a routine matter, verified that the method is working properly in its hands by showing that when items with known quantities are measured by this method, the method produces the right answer. So correct results with known standards is called calibration. A third issue that lawyers need to think about is reliability. How consistent are the measurements made by the method? Is there random error in the results such that when the method is used to measure the same thing multiple times, you get different results? So suppose, for example, that a lab is measuring the blood alcohol concentration using its methods, and it tests the same sample 5 times, and it gets these results. 0.09%, 0.08, 0.07, 0.06, 0.05. Obviously, if there's this much variation when measuring the same thing, there's not a high level of reliability, and it raises concerns about how much we should trust any single measurement. If a second instrument was used and measured the same sample and got these results, we're ranging from 0.0802 down to 0.0798, that would show a higher level of reliability. We would trust more that any particular measurement was close to the mean measurement that you'd get if you measured the item multiple times. So we could trust these a little bit more. Although note that measurement error and calibration aren't the same thing. So a test could be very reliable but poorly calibrated. Notice the mean measurement here is 0.08, or the mean measurement here is 0.07. If the actual blood alcohol concentration in the sample was 0.07, it may be that this method, although unreliable, is well calibrated on average. This method is much more reliable, but poorly calibrated. Calibration and reliability both have to be considered. When considering reliability, there are two statistics that are important for lawyers to consider. One statistic that you'll hear a lot about is the standard deviation, which tells you how much variation occurs in measurements when the same item is measured multiple times. So this chart shows a distribution of measurements. It could be measurements of blood alcohol concentration or any other quantity a lab might measure. The x-axis along the bottom shows the quantity measured. So if you measure a particular item multiple times, you might get a range of measurements from low to high. The y-axis shows the proportion of all measurements at each level of quantity. All right, so what percentage of measurements of the same item fall at each point on the range. When the same item is measured many times, and there's some random error in the measurements generally tend to cluster around the average value in the middle. That's because big errors are less common than small errors. So the proportion of measurements at a given level gets smaller as you get farther from the mean, either higher or lower than the mean. You get lower, you get a lower level of measurements there. And this creates what statisticians call a normal distribution of responses. For a normal distribution, one standard deviation shows the distance you need to move along the x-axis above or below the mean to include roughly 2/3 of the measurements. So if you take the mean value of all the measurements and you go up one standard deviation or down and down one standard deviation, that would include roughly a little over 2/3 of all the possible measurements. If you go up and down 2 standard deviations, that includes roughly 95% of all the measurements. 3 standard deviations would include about 99% of all measurements. To illustrate, let's suppose that we measure the blood alcohol concentration of a particular sample many times, and the mean of all our measurements is 0.08. So here's the mean. And let's imagine that the standard deviation of the test is 0.001. The Greek letter sigma is often used to designate the standard deviation. Okay, so what that would mean is that roughly 2/3 of the observations would fall between 0.079 and 0.081, and roughly 95% between 0.078 and 0.082, and that would give you a rough sense of how much variability you would see in these measurements. Another statistic that is useful for understanding the amount of random error in measurements is the confidence interval. It's useful if you want to know how far a given measurement might be above the mean that you would get if you took many measurements on the same item. So to compute confidence intervals, you need to have done research to establish the standard deviation in measurements. To illustrate, let's suppose that the blood alcohol concentration that the lab reports is 0.083. What are the chances that this measurement is artificially high due to random measurement error? And if the lab were to measure the same sample again multiple times, that the mean of all those measurements would be 0.08 or lower. And this one sample just happened to measure high due to random processes. This could be important to know if 0.08 is an important threshold for legal purposes. The confidence interval is a range of values around a given measurement, often given as plus or minus some value. And the range is drawn so that it has a certain specified probability of including the mean of whatever distribution the measurement was part of. So it's common to report a 95% confidence interval. and that's the range of values that's wide enough. It's wide enough to have a 95% chance of including the mean value that you would get if you measured the same item many times. You sometimes also see a 99% confidence interval, which is wide enough to have a 99% chance of including the mean value that you would get if you measured the same item multiple times. So, to illustrate, suppose that blood alcohol concentration is measured to be 0.083%, and the 95% confidence interval is plus or minus 0.002%. Okay, what does that mean? That means that if you tested the same sample, the sample where you got the report of 0.083 concentration, if you tested it many times, there's estimated to be a 95% chance that the mean of all of those measurements would be plus or minus 0.02% from this value. So there's a 95% chance the mean would be between 0.081 and 0.085. And that tells us that it's unlikely that random error would produce a measurement as high as 0.083 if the true blood alcohol concentration was at 0.08 or lower. Important to know. To summarize, when looking at cases where labs are presenting a quantitative value, lawyers need to consider several things. First, has the method been validated? Is there a published literature demonstrating the validity of the measurements? Second, were the measurements appropriately calibrated? Has the laboratory kept records that show that the instruments that were used to make the measurements perform correctly with known standards under realistic test conditions like those that were used in the case? And finally, there's the issue of reliability. Has the laboratory done research on its measurement error? Do they have a valid basis for estimating the amount of measurement error? And have they taken proper account of measurement error in drawing conclusions in the instant case? Those are the questions that lawyers need to have answered to have a sophisticated understanding of what the laboratory results mean and what their strengths and limitations might be. That's all for now on quantification. In the second video in this series, I'll be talking about the statistics and probabilities that underlie another forensic science task, classification. And in the third video, we'll be talking about comparison and identification.